Hey guys, Shreyas here, and today we are in the 15th day of July LeetCoding challenge, and the question for today is valid triangle number. And so the question says that we are given an integer array, and we need to find the number of triplets which we can choose from this array, such that they can form a triangle if they are assigned to the side lengths of the triangle. So that's the question. Over here, there are three triplets. These are triplets. So first of all, we need to know the rule for any three integers to form a triangle. So the rule is that the sum of any two lengths should be greater than the third length. And so that's the rule. For example, over here, 2 plus 5 is greater than 4, 3 plus 4 is greater than 2, and then 2 plus 4 is greater than 3. So a sum of any two side lengths is greater than the third side length. So that's the rule. And the constraint is small, so it's a hint that n square solution will also pass. And so first we need to discuss the advantage of sorting the array. So first of all, we notice that an n square solution would pass the time limit. So and sorting takes n log n, and so we need to discuss the advantage of sorting first. So the advantage of sorting is that, suppose we have an array over here, like say 2, 5, 6. So this is a sorted thing, right? And we know 2 plus 5 is greater than 6, and so we check condition for 2 and 5. We need to check remaining two conditions, but there's no need for us to do that, because we already know 6 plus 5 will be greater than 2, and then 6 plus 2 will be greater than 5 in a sorted manner. So that is the advantage of having a sorted array, that we need to check only for one pair of triangle side lengths and not all the three. So like 2 plus 5 is greater than 6, and that is enough, nothing else. So that's the advantage of sorting. And the brute force solution is just to exhaustively check for all the triplets by running 3 for loops. That's a simple approach. By running 3 for loops, check if the condition is satisfied by all the triplets. Count the number of triplets which satisfy the condition or not. So that's O of n cube, but it will not pass the time limit because it's like 10 power 9. It's too much. So in order to optimize this approach, we have a hint that we need to sort the array, and so it's an intuition for us to use binary search in this problem. And how binary search works is that, for example, just a second. Okay, so suppose we are in this position I and j. So these are the two side lengths of the triangle, and we need to determine the third side length of the triangle. Earlier we used to go all the way, exhaustively check for all the remaining elements, but since the array is sorted, we can just binary search for the summation of the number at I and jth position. For example, over here we can binary search for the number 9, and it would return us this position. And hence we can easily say that 6, 7 and 8 will form a valid triangle. Any number among 6, 7 and 8 will form a valid triangle with 4 and 5, and hence for the pair 4, 5 there are 3 options for us. So do binary search for all the pairs. For example, if you do binary search for 4 and 6, the position for 10 in the binary search would return us this position, and so we can confirm that any number from 7, 8 and 9 would form a valid combination with 4 and 6 to form a triangle. So for the pair 4, 6 also we have 3 options. So for all such pairs, we find the number of such options we have for forming a triangle, and return the summation of all of those. So the time complexity for this approach would be, first of all, we are just exhaustively checking for all pairs, so that is O of n square, and for each pair we are doing a binary search, and that is log n. So we have reduced the time complexity from O of n cube to O of n square log n. So that is the optimization we did, and the code for that is quite simple. So exhaustively check for all pairs of I and j. Check for all pairs of I and j, and for each of the pair, check for the index with the value greater than or equal to the sum of those at ith and jth positions. So lower bound is a binary search implementation that returns the position iterated to a position where that number is greater than or equal to the number we are searching for. We are searching for nums I plus nums j, so it will return us the position where the number is greater than or equal to this number, nums I plus nums j, and whatever the difference is there, right? So whatever numbers are the count of numbers in the difference of those ranges, we can take that as the third side and form the triangle. Do that for all the pairs and return it. So this is the O of n square log n approach, and the way we optimize, and this is a good enough solution for us to pass. For example, over here you see so this passes all the test cases, but the runtime is very poor, like around 600 milliseconds. So the most optimal approach is based on some observation, which I'll be telling now. So the idea is almost similar to the last one. We exhaustively check for all pairs I comma j, but suppose we are at a position k over here, and for earlier we used to binary search for 4 plus 5 is equal to 9, and we used to take, so we confirmed that any of 6, 7 and 8 could be included in the answer, could be included in the triangle. So over here what we do is and then in the next iteration we again do one more binary search, right? So but here we won't be doing that. So in the first, for the 4 comma 5, k stopped over here, right? Because 4 plus 5 is not greater than 9, k stopped over here, and we took 3 for that pair. And for the next pair, when j becomes 6, now j is 6, so now j is 6, and the question is, like, do we really have to check for 7 and 8 once again? Previously 7 and 8 qualified for becoming a part of the triangle, and again for the new pair, do we have to really check if they qualify once again or not? The answer is no, because like since 4 plus 5 is greater than 7 and 8, obviously 4 plus any other value greater than 5 would also be greater than 7 and 8, right? So we need not recheck again for 7 and 8, and hence that is how we can save the computation time. So whatever was already satisfied will satisfy for any other pair as well. So we check for k values where we are stopped from the last time. So this was the index where k was stopped the previous time, and hence we start checking for k values greater than or equal to this index. So 4 plus 6 is greater than 9, so increment k, and but 4 plus 6 is not greater than 10, so again stop k over here. So and for pairs 4 comma 6, the answer is these three numbers. So the concept is based on reusing the k values and not starting k from the beginning once again, and so that's the approach. more things will be clear in the code, I guess. One second. So I just initialize k for for all values of I, and for j values of I plus 1 till n, we are using only 1k and not initializing k again and again for every j value. So initialize k to I plus 2 and just increment k till wherever this condition is satisfied, and then increment the answer for that all the numbers in that range, right, k minus j, those will satisfy to be a part of the triangle, and hence add them in the answer. So this reduces the time complexity from, so over here we are not doing a binary search, but we are iterating k only once for each I. So the time complexity for this one would be like O of n square plus O of n square, because k is like the distance traveled by k is equal to distance traveled by j. It's j, they are the same. So for I comma k it is O of n square, for I comma j is also O of n square. So the total time complexity will be O of n square only. And so that is how we optimize from O of n square log n to O of n square. And the space complexity, if we consider sorting in the, if we consider the recursive stack used by sorting, we can just say, like, to be more approximate, we can say space complexity would be like O of log n, but that is too negligible as well. So we can just neglect it. And but the interesting thing is, like, with binary search it took 588 milliseconds, but with this most optimal solution it took only 124 milliseconds. So this optimization, like, is really helpful. And so those were the 3 approaches for this problem, and thanks for watching the video.